stream. I probably need a terminal, maybe. What's my OS currently doing? Oh, I can type. That's crazy. Okay, look at this.
Whoa. Look at that.
Look how exciting this is.
Letters.
Yeah, and I think spacebar works too. No, it doesn't. Okay. Oh wait, no, it does. It does. It does. The flashing doesn't work because we couldn't figure out how to code flashing. Remember? So, oh, what? Did you? There's lower cases in there?
What are you typing that does that?
I'm just going.
Are you? Is that being?
It's when I hold down colon. Oh, it's colon. That's colon. Yeah.
Okay.
Oh, so I don't have special characters bound, I bet.
Looks like.
Yeah, there's period.
It's not a period.
That's a question mark. Oh, here's right shift.
Ooh.
So the trick is to only use Latin characters. So you can say hello world. That's fine. Because I didn't code any of the other special characters because I wasn't planning on using them.
What do you need other than?
Yeah, no, there was like all this stuff. There was all this stuff in blog that was like, don't you want to set up a crate so you can type? And I was like, no. I'll just like, if there's a character, like a keybind that I want to do something, I will just program that keybind, right? So anyways, that's what I did. So anyways, without further ado, paging. I think, if I remember correctly, my brain sort of just has stopped working at this point. I don't know if any of you have experienced this. It was like 72 degrees yesterday, and my last two neurons stopped talking to each other. They're like, we no longer have time. Welcome back. I'm pretty sure you should be getting the keyboard working like I just demonstrated. I could have written an extensive testing function that makes sure your keyboard does interesting things. Here's a fun fact. Think about this for a minute. Could anything possibly be less interesting than programming the shift key for your OS? Like, how could anyone possibly care about that, right? Like, you know how to do it, right? Like it's like 4 lines, but you like have to debug it by launching a QEMU window. Like, no one wants to do that, right? So that's why I didn't do it. I like my letters are uppercase. I don't care. Timers are cool, right? So I think setting up the timer will require some non-trivial amount of thought. It would probably be interesting, and I think writing a clock would be really interesting. So that's why I gave you that as an assignment. Playing around with updating the VGA buffer in a way other than is directly supported by print line is an interesting thing to do, in my view. So having a timer that actually rolls over when things happen, that seems cool. We're no longer doing any of that stuff, but many times today I'm going to say, oh, we solved this problem just like that other thing we did with interrupts or with exceptions or so on. So we're going to do paging, and to me, paging feels more basic and elementary and foundational than interrupts and exceptions, but it kind of doesn't make sense to teach it before interrupts and exceptions because a lot of the things we already had to learn for interrupts and exceptions we're going to use to teach paging. So for that reason, we are sort of now getting to the most basic thing an operating system does, which is, of course, organize memory. We can imagine a case where a computer could do interesting things without having any support for interrupts or exceptions. We probably cannot imagine an interesting computer that does not have memory. I would, so I've talked about there's different ways to teach these things before. I'm going to just, on this slide and never again, reference something. There is a fairly, I think, foundational, in my view, problem in what I thought was algorithms, and now I'm realizing that this actually might be industrial engineering. Remember when we talked about industrial engineering the other day? This might actually be an industrial engineering problem. The bin packing problem. So the bin packing problem is, given some polygons or some numbers and some containers, and perhaps the containers have a maximum number, or perhaps they have some space in n dimensions, right? How can I fit my polygons or my numbers into these containers? To me, that feels like the energy organization problem. So perhaps writing operating systems is an industrial engineering topic. I don't know. I never really thought of it that way. I always thought of bin packing as a really fundamental computer science thing. I'm assuming either no one has taught you bin packing or someone has already taught you bin packing, and in either case, I'm not going to teach it now. But I'm going to let you know about the bin packing problem. I have a link to it. I would encourage you as a computer scientist to be familiar with the bin packing problem if you haven't heard of it before, if you haven't looked into it. It's a metaphor that comes up frequently. Instead, we're going to talk about paging. There's one other metaphor that's going to come up today. I'm going to mention a radix tree at some point. I'm going to just assume familiarity with that. Radix trees are cool, but I don't think you need to actually know what they are if you don't already. Okay, so I'm just going to give you a sketch of what we're going to work through today so you sort of know where we're at. The way to motivate paging is to show that what look like simpler and easier solutions introduce problems. And these problems are usually not theoretical problems. They are not problems that are fundamental to how computers work. We do not have to assume, for example, infinite memory to get something to work in any case. They are really operational problems. They are problems that impact the efficiency of using actually existing physical hardware, even though theoretically we may not care about that, or it may not actually be a real problem. I always thought, sort of in the reverse about paging, is that paging is a very good data structure solution to a real problem that actually exists. And if you have a data structure as good as the page table, which we will get to, it doesn't really make sense to me to ever use anything else. So I think paging just sort of hits this Goldilocks level of like optimality and efficiency. But we're going to show some other examples to motivate it. Okay, so I skipped to the end. I wonder what key I hit. I don't know. Okay, so the first thing we're going to talk about today is memory isolation. I think memory isolation is relatively easy for computer scientists to understand, and I'm going to demonstrate it using our favorite language that is not a programming language, Python. And so the way I'm going to demonstrate this with Python is I'm actually going to write some Python. I'm sorry, I know you all hate it when I do this. I'm going to take a variable named x, and I'm going to set x equal to 1. Then I'm going to create a function. I'm just going to call it f. And within that function, I'm going to set x equal to 2. And then I'm going to print x. When I f, I'm going to see the 2, even though the x outside is still a 1. This is often taught in programming language theory as being about namespaces, right? And it is, in fact, about namespaces. But the namespaces are themselves a form of memory isolation. Inside the function f has a distinct stack frame. It does not necessarily have visibility to external values or external memory. So when I look at x inside of f, it is not impacted by the x outside of f, and vice versa. So there is memory isolation between the global namespace and between the functional namespace. In this case, we're not actually truly isolated, but we can come up with an isolated example. So if I redefine f to simply print x, then it will look at the global x. But if I delete x, and then I create a different function, g, that defines x to be equal to 2, in this case, I do have successful memory isolation, even though there is a defined x in the context of g. So I can run g, and that will define an x and do nothing else. There is memory isolation in between the g namespace and the f namespace. So even though there is a defined x, I execoded code that defined x, I cannot see this x from inside of f. So it appears from the visibility of f, x does not exist, and it is also true from the global namespace. There is no x that exists, right? This is an uncomplicated topic that you are familiar with. That said, I think we are mostly familiar with it in the context of a single program, oftentimes within a single programming language. Now, when you are an OS, you have many responsibilities. You might have to run programs in many languages. You might have to run executables. You might have a scripting environment that's running. You might be supporting a read, evaluate, print loop, which I will never remember what those letters stand for. The OS is responsible for isolating different programs and ensuring they have internal memory coherence and also that they are not corrupting each other's memory. So no one is messing with my memory, and I am permitted to mess with no one else's memory. This is the simple memory isolation thing. A lot of times I think this looks most immediately on its surface like a security concern, right? You don't want someone else messing with your bits. I think this is a sort of a restricted understanding of how useful this is, which is it would be basically impossible to write any code that makes sense at all if you couldn't assume the internal consistency of your own memory space, right? So this perhaps looks like security, but this is actually a case where functional correctness would be dramatically adversely impacted if we could not guarantee memory isolation. So here's an example that you may be working on right now. You may have two globally visible memory locations. One of them may be a clock, and one of them may be a VGA text buffer. It could be the case that you want some program to have access to one or both of these. It is most likely the case that you are going to want to have no one except the timer handler to have read access to the global clock. So somehow you're going to have to isolate that from other users somehow. Currently, we've been solving this problem by throwing static mutes at everything. That's probably bad. I should give you an example of this in a sort of, consumer-grade OS, like the OSs we work with. It is generally the case that if I try to open a local file from my file system in my web browser, and especially if I upload it rather than just use it as like a PDF viewer or something, that probably my operating system should be the intermediary in that operation. I do not necessarily want a website that I visit on my computer to have access to the files on my device. The files on my device can contain things like, I think I have like a copy of like some tax documentation, right? And for the record, I would like to state that I probably paid my taxes this year. And so since I probably paid my taxes this year, there's probably some evidence of that on my device. At some point, some of that evidence probably had to make its way into some web portal or something, but it probably doesn't want to go on, what's the website called now? The site formerly known as Twitter. But it probably does go to like Oregon.gov or something, right? Which are my two favorite websites to visit. I visit both of them every day. The same thing is true with video players and so on, right? So I have a number of sort of local utilities on my device, and then I have access to network. So how are we going to achieve memory isolation? Well, memory isolation is a big enough deal that it comes with a fairly robust hardware support. This isn't too surprising. You have to use hardware for something. We have already had hardware support for some things that looked an awful lot like software to me, so to me it seems like divide by zero should be something you can handle with software. Well, maybe you can't because the divide operation is hardware level, right? So hardware is going to have built-in support for memory isolation. Perhaps this should make a little bit sense to us because memory is hardware, right? Those bits are somewhere physically, and so we're going to be dealing once again at the hardware-software interface. Here are some physical things that are going to happen. If I have a program on my computer, if I have VLC Media Player, or if I have, is iTunes still a program?
Yeah.
Okay, cool. Good for Apple. Or we do not have to hand it to Apple. But okay, so iTunes is a program. There are, all of the programs that run our command line utilities. So I don't know. It's good old World of Warcraft. That's a good one. So all of those are going to be written as a string of bits somewhere on a solid state drive or perhaps a hard disk drive on my computer. When I run those programs, when I actually use those programs, I am going to copy them out of the solid state drive and put them into my physical RAM, my random access memory, my main memory, of which I have probably 16 or 32 gigabytes, right? Now, every single program that runs on my computer is going to use the same physical RAM, which means it could be the case that if I do not manage my memory isolation correctly, whatever is currently in RAM is visible to everyone. So if my tax documents are currently open in my PDF viewer and my web browser is currently scrolling Instagram, it could be the case that it is a little bit too easy for Instagram to look at what is currently in my RAM and see my tax documentation. So, how are we going to solve this problem? We're going to introduce the sort of idea, or the abstraction, of virtual memory. Virtual memory is going to give numerical keys to each of the values that are stored in actual physical memory. We are going to use these keys to keep track of where things live and what permissions they have. But as soon as we do this, we are introducing overhead, and now every memory access comes with some form of cost, and that cost must be paid by the operating system. The operating system will be responsible for managing the memory. We are going to begin by looking at a non-conventional way of doing this in the sense of consumer-grade CPU. So the ARM Cortex-M processor, I think we used it earlier this term. Maybe it was one of the first things we booted anything on. I think we maybe ran bare metal on it like the first week of class. So I've definitely run into these, and I think I've run into them in my research as well as this class. It's a common embedded platform. This is what their die cast looks like. I don't really expect any of us as humans to be able to look at a die of a CPU and actually infer what we're looking at, but there's a picture of it. There it is. Yeah. Integrated circuit die photo of is that number of letters really necessary? Yeah, it probably is actually, right? Has motor control. It's ancient. Oh my gosh, it's from 2012. Okay. 2012. Who's the Speaker of House in 2012? I'm hitting John Boehner. We're checking. Oh! I'm incredible. So I don't know how old all of you are. In the olden days, this is the first politician I remember being made fun of for being orange. Right? So we currently have an orange politician. This person was considered orange at the time. And look how not orange this person is compared to our current orange person, right? The innovation in orange politicians it's increasing, folks. I mean, we're probably going to have the Lorax elected president in the next 5 years, right? Well, but the Lorax will speak for the trees, so it'll be okay.
I wouldn't mind the Lorax.
I would vote for the Lorax.
Yeah.
The question is, would the Lorax vote for me, though, right? So be the Lorax you want to see in the world. Okay. There's more than one way to protect a memory. And one way to protect a memory is with a memory protection unit. You probably should have some intuitive sense of what this is. You know what a central processing unit is, and you know what a memory management unit is. A memory protection unit, it's probably not that bad to visualize it as perhaps some intermediary between the CPU and the MMU that lives on the bus. And what's it going to do? In the case of the Cortex-M, Cortex? What is Cortez? That's someone's name, right? Is it, or maybe like a semi-precious gemstone? No, that's quartz. Okay, we're gonna say Cortex.
Coffee place.
It's a coffee place?
Yeah.
Cool. Shout out Cortez. Okay. So the Cortex-M has an MPU. The MPU is programmable. It allows software to configure 8-ish, plus or minus, it doesn't actually matter how many, right? Regions of memory. Why do we say regions? It, to me at least, makes sense to think of memory geospatially because it used to live on tapes, which are linear, easy to think of geospatially. Then after that, it lived on hardware drive platters, easy to think of that geospatially. And it's actually not that bad to think of a solid-state drive as containing transistors and ranged in 2 or 3 space, and you're just talking about a region of them. So at software level, we can also think of them as regions. We can, for example, think of this as taking a two-dimensional slice of an array in NumPy. Right? Regions can be differentially permissioned. I think of this as read, write, execute. I don't think that's actually what Cortex supports, but we'll have some read permission, we'll have some write permission. You know, it makes sense to have some read-only memory. You can throw the BIOS in there, right? And the place that makes the most sense to put this is in between the CPU and MMU. And so what happens when the CPU makes a memory request? It's going to make some read or write request. Instead of that read or write request going directly to the MMU and the MMU instantly executing that request and serving the bits back or caching the bits or whatever it's doing, the MPU will vet the request and will verify that no writes are going to read-only memory and no reads are going to write-only memory and no executes are coming from non-executable memory and so on. So we completely farm out the memory isolation problem from the OS. It's simply handled by a piece of hardware. And I think that's great if you're a microcontroller from 2012 and you don't have to do any high-performance computing. But we are not a memory controller or microcontroller from 2012. We're working on x86, which is my goat. What a great architecture. There's absolutely nothing wrong with it. I know Jimmy's been doing like daily unraveled posts about how much more sense RISC-V makes, and that is true. But it's also true that no code runs on RISC-V. So pros and cons. x86 has two main options. They got the old option that kind of worked well enough and is no longer supported at 64-bit, and then they got the new option that's the purpose of class today. This is an OS class, so you need to know about both options. Okay, so the first option is segmentation. When I say segment, what I would like to happen to you is you think immediately, I remember discussion of the code segment register, the data segment register, the stack segment register, and the ES, FS, and GS, which are three different extra segment registers. I remember when we were dealing with interrupts, we would change which segment we are working in before running the handler code, because we would change from a potentially user-level segment to a kernel-level segment. And you probably also remember with your double fault handler, you were changing stack segments so you could get a fresh stack that was not blown up by infinite recursion. So you're changing segments somehow. So you should have on some level some sense of what a memory segment is. It's some kind of chunk of memory. And it's some kind of chunk of memory that has really robust hardware support. But the other thing you may want to be thinking about is that when we discussed the segments, we often discussed the segments in the context of 32 and 64-bit devices, where many of the things that were present in our segments were holdover or legacy code from 32-bit mode that was no longer supported. So the alternative to segments is paging. Paging, rather than relying on sort of this pure hardware implementation, is going to rely on a little bit of a friendly handshake between the operating system and the hardware. The hardware is going to continue to process all memory accesses and memory requests. However, in the process of processing those requests, it is going to look at certain memory locations and expect there to be lookup tables there. This is identical, practically, to the interrupt descriptor table, to the global descriptor table. We have already, as the OS, taken responsibility for writing certain memory locations, writing at certain memory locations pointers to other certain memory locations. We have populated tables with pointers to functions. Paging is kind of the same way, it's just for data instead of instructions. Here is a description from some website. This is either OS Dev or Wikipedia. I have no idea which one. Okay, this one's Wikipedia. Page tables are used to translate the virtual addresses seen by the application. I would not say seen by the application, right? I would say software visible. These are software visible memory locations. Whenever I print out in hexadecimal the location of something in memory, I am getting back a virtual address because I am acting as software at that time. So from the level of my visibility, I am seeing a software visible numerical address. That software visible numerical address can correspond to a number of different things, but most importantly, it can correspond to something that is currently residing in the solid-state drive or currently residing in main memory in the RAM. And someone, you, the OS, has to keep track using something, a page table, a data structure, how to translate a virtual numerical address into the physical address, which again could be in different places in physical hardware. And then once you have this physical address, then you can carry out your memory operations. So first we are going to learn about segmentation, because segmentation is academically interesting and you should know about it. Segmentation is super old. It, I guess, was introduced in 1978. How old is that? I think Unix was just getting its right to vote that year. I think Unix is from 1960. But the first commercial release of Windows I'm aware of is 95. There was MS-DOS before that. So this is the intermediate point between Unix and Windows, right? So about that old. Why was it introduced at that time? Because right around that time, there was starting to be enough memory that it made sense to actually have some memory organization. And I'm not saying isolation in this case. Very early devices had such little memory. Everything was hard-coded to physical, numerical, literal, whatever, addresses. It only became necessary to introduce this idea of segmentation later on when you can index more than 256 bytes, right? So segmentation was introduced as memory sizes increased in order to make it easier to utilize that extended memory. So at some point in time, you might have more memory than you can, for example, address with your U size if you're on an 8-bit device and you have more than 256 bytes to work with. In particular, in 1978, I guess it was pretty common to be 16-bit at that time. I don't actually have a sense historically for when the change from 8 to 16 bits happened, but it had to have been very early. 256 is a very small number, right? And then even after that, I think it took forever to get to 32 bits, because I believe all of the gamers when I was a child, they were still playing on 16-bit devices. So I think Super Mario 3 is like a 16-bit game. If you only have 16-bit addresses, you can only work with 64 kilobytes. And 64 kilobytes is not enough to store the Gangnam Style music video in high definition. So this was insufficient memory for practical purposes. So, what do we do? You still use 16-bit addresses, but each process uses its own 16-bit addresses. And each process exists in the context of some segment, and each segment has its own potential 16-bit address. So we can now sort of nest these things. We can have locality and local space. Then within actual physical memory, each one of the segments corresponds to some different offset or distance from some baseline. So every time the CPU and the MMU together are processing some memory instruction given a certain process, they will take the address from that process, which will be 16 bits. They will prepend to that process some segment address. And when they put that segment address on the front of the process address, then they will get a full, perhaps 32-bit address, and that 32 bits is sufficient to address all of system memory. You have seen this before, because when we were dealing with our execution handler, or our exception handlers, we had to set both a pointer and a segment to correctly jump to certain locations. So you're familiar with this. With all these techniques put together, you're able to look at 1 megabyte of memory. Those of you following along at home, what is 64 squared? 64 is 2 to the 8th. No? 6th. I'm saying 6th. Does anyone like 6th? Okay. So that's 2 to the 6th. And what's 2 to the 12th? So 2 to the 12th is 4096. So something is going on here, because I would expect... Is there rounding? I would expect you to be able to get to reach the square of this, right? So it probably takes 16 bits to address 2 to the 56. Well, let's see. So you can address that many unique situations. And then I would have thought, I don't think this is going to be a megabyte. Right? I don't understand why you can only access 1 megabyte. I would really expect 4 megabytes. So they're using some bits to store something somewhere. Is my computer making all those noises? Sorry, I had to watch some YouTube streams during lunch, so I had my sound on. You know how it is. Are any of you able to eat without YouTube? Yeah, like I sit down to eat and then I'm like, oh, I'm like using my hands to do something unless I put YouTube on. And then like when YouTube's on the computer, I'm like, YouTube's taking care of my computer. Now I can use my hands to take care of me, right? Like it's sort of like a co-parenting situation where like YouTube does childcare, right?
I'm the iPad baby.
You're the iPad baby, okay.
Because I needed to use it.
Yeah, it's like here's YouTube. Now eat your Cheerios or whatever babies eat. Yeah. So I was looking at a baby this weekend, as one does. They're around, right? And this baby introduced this really interesting technique I hadn't seen before. So we all know babies love Cheerios. No one knows why. But baby poured Cheerios on the grass and then ate them out of the grass. This has to increase the nutritional content of the Cheerio, right? So, like, baby's, like, so much smarter than me. So I was thinking, and I didn't do it today because I just thought of it now, I should start tossing my sandwiches in the grass before I eat them to get more nutrients. Okay, segment registers, you've seen these before. I told you about these already. There is a link here because I'm worried you won't believe me. I told you about, the link, is the link cursed? CS code segment? Code segment? Okay. I'm like 100% sure I've taught you about code segments, right? See, the region where the currently executing code lives, was possibly anywhere, is now where the OS keeps exception handlers. Remember these things? You remember the segment descriptors? Okay. So segment registers are back, and segment registers are back. Also, there's one clever thing I would like to point out on this slide. I think it's very cute that they named the extra segment EF, SS, and GS, so I call them the extra, fextra, and gextra segments, right? That one's free. I'm sure other people have done this, but I haven't seen them. But I bet if you drop gextra in a job interview, I would hire you on the spot. I don't know that anyone else would do that, so it's possible this is bad advice. These things used to be easy to use because they were mandatory and everyone used them, and all programs assumed they were used, and also all of the OSs were 32-bit, and it was pretty easy to add them together. The segment registers in the olden days. Do I have it up here? So they have this thing in here called the base address. Notice how it's 16 bits, right? And actually, you can go up to more bits than that if you want. See, they figured out a way to make it go up to 32 bits, so this was nominally going to support 64-bit segments for 32-bit registers, right? And all this stuff is kind of non-contiguous, which means that somewhere inside the CPU, the physical CPU, there has to be wires that are hooked up to this that are going to put it in order somewhere else and use it as a prefix for something. So we've got these segment registers floating around. And in the olden days, whenever your code was running, there was some populated segment register every single time a memory access occurred without conditions, so deterministically. That memory address had the segment base address prepended to it, and then it would operate as a fixed offset into physical memory. And this was a good way to achieve memory isolation because you could give 64 kilobyte chunks to everyone, and there was no possible way those 64 kilobyte chunks could overlap unless the segment registers contained the same values, and then all you have to do is make sure they're not the same. Then there's protected mode. Jimmy, do you have a take on protected mode? Have you gotten into protected mode ever? Okay, all right. Protected mode is two things, right? So, okay, let's pop it open. So, protected mode was a big thing for a while. Let's see. It's now been replaced by like real mode. What's the current mode everyone uses? I don't know. It was a 32-bit
Long mode.
long mode. That's right. It was one of the 32-bit modes, I believe. This is saying 82. Yeah, I think that's, yeah, 32. To my knowledge, protected mode is the first time the metaphor of there being separate kernel and user level programs was codified in hardware. So there were actual bits in the hardware that said whether you were operating at user or kernel level mode. And so protected mode is historically interesting for that reason. Alongside this change, a lot of memory accesses got a lot more interesting in that they became more conditional. So once you have hardware support for kernel and user level mode, you can now have hardware support for kernel and user level memory protection. And what this meant is that the segments were no longer fixed offsets, but they were now getting passed through some intermediary. And that intermediary passed through the global descriptor table. So now, what we have for the first time is we have hardware support for programmable memory control. This is why it's called protected mode, because the OS can now protect regions of memory. It can set aside regions of memory exclusively for its own use, and then it can also denote regions of memory as usable for user-level code. We have done this already. When we handled the double fault, we passed through the global descriptor table, we changed our segment, because we wanted to switch to a new segment that we knew was kernel level, and that we knew did not have any other executables running in it. So we've already done this. We've already, I'll say, maybe exploited or benefited from protected mode in handling our double fault. So protected mode protects the memory. Who does the protecting? The OS. Now the OS gets a lot of help from hardware. It would be hard to do this OS only, but you could do it OS only if you wanted to. And the way you would do that is you would take all memory accesses and forcibly pass them through hardware, or through software. Okay, so I'm now going to pretend I'm a program. The program I'm going to pretend to be is, what's a program I use? I feel like the only program I ever use is calculator. So I'm pretending I'm a calculator. Since I'm a calculator, I'm user mode. I don't need to access anything on the device, right? So anything you've ever written outside of this class, maybe your CS 151 or 152 assignment. In CS 152, do you make any applications?
Don't think so.
Okay. And then we made a version control app last term. So yeah, I'm your version control app, right? I'm running at user mode, and at least my version control app, it was writing in memory all the time. Remember, I had that like enormous JSON file that I took a lot of effort to make sure it wasn't self-recursing and therefore infinite in size. So that was a good time. So my version control app felt like if I ever wrote something to memory, I could read it back from memory and I could get the same value. Internally consistent memory. No one else was monkeying with the memory I was working with. Now, at least with my version control app, this was actually a slightly sketchy claim to make because I was writing into the file system, and I didn't actually own those files. So it was, in fact, the case that my version control app was able to edit itself, which was, maybe that's bad. You're not supposed to write self-modifying code for some reason because it's, hard, I think. So whenever I write applications, those applications assume that if they set x equal to 7 and then run for 10,000 years and then come back and look up x will still be 7. So at a software visible level, there is seemingly internally consistent memory. I don't have to think about anything other than memory addresses. I assume, unless I am doing intentionally some form of concurrency, that no other program is writing to my memory space. And usually for interprocess communication, you're using signals or pipes or networks or something cool like that I get to teach in 2 years. So any write persists to be read, and it probably persists past read unless I delete or free. And the OS is responsible for making sure this happens. So if my program starts running, evaluates a halt loop, goes to sleep, and is woken up 10,000 years later, it is the responsibility of the OS to make sure that all of the things that were in that program's stack frame persist through that time, and when it resumes execution, the program has no way to perceive how long it's been running and what else has been running on the device. So, when the OS is running, it should not make any software visible changes to memory regions that are visible to any user level code. You have seen this before because you have written code that segmentation faults. And what is occurring when a segmentation fault is happening is you are looking at a memory region that would potentially contain software visible alterations from the OS or from other programs. And so the way the OS enforces memory isolation is when you attempt to make an access to those memory regions, it terminates your process. At least for me, like the first time I hit a segmentation fault, I was like, oh, that's so annoying, why does I do that? And now that I actually write my own programs, I find it extremely convenient that my OS is preventing me from reading things that I didn't write, because I probably don't want to be writing them. Okay, that's segmentation. We all love segmentation. I'm not going to ask for applause for segmentation, but in your heart, I think you should applaud segmentation for getting us to where we are today. Now we're going to get to virtual memory. Virtual memory is like segmentation if you had atomic segmentation. Okay. Let's step through what virtual memory means. Virtual memory is this kind of like non-trivial topic to introduce for the very specific reason that exclusively when you're talking about virtual memory and physical memory, you have to put an adjective in front of address. I think pretty much at every point in your educational career until this point when we referred to an address, it was clear that it was just some numerical description of a location. Now there are going to be multiple numerical descriptions of locations, and there's not even going to be bijection between the two numerical descriptions. So how does this work? Whenever a program uses a numerical memory address, the reason it is using a numerical address is because prior to 1978, those memory addresses referred to probably your distance from the start of the tape. And code, for backwards compatibility reasons, has preserved this usage where the lowest memory begins at 0 and then it increases linearly to some limit. This isn't necessarily a bad way to do things, but it is not necessarily the way things work in practice now, since most of your memory is stored in random access. I think of it as follows. In the modern era, I do not think of memory addresses as numbers. I think of them as an opaque, bit-packed data structure that happens to be the same size as your bit size, so your U size. And portions of the data structure incidentally contain what appears to be linearly increasing memory addresses. But other regions do not. Other regions are sign extended or something else. So really what you're dealing with is a data structure, but you are not supposed to know it's a data structure. And so whenever we see it, we're going to just somehow be probing some sort of system internals to get a numerical address back. We all know my favorite programming language allows you to do this. So Python, for example, can expose memory locations in some sort of bizarre way with the ID function. What is ID?
Bulletin would be my guess.
Yeah. By the way, you all know I'm a hater.
Function or method.
What do you mean function or method? What do you mean function or method? Right? I thought that would work. Oh, wait, no, I think I have to do this.
You have to wrap it in that, yeah.
Int has... Oh, is
I'm
it...
assuming plus just isn't the name of
Yeah.
that operator.
Oh, it's a method wrapper?
Well, yeah, because it's the underscore version, not the... I don't know. Maybe that's what they call those overwritable ones.
Yeah. Oh, there's no way you can overwrite this.
Oh, you can? Well, they're probably... actually, that makes sense. They probably... hope no one ever does something like that, yeah.
Hold on. I think we should write some code real quick. I'm having fun.
Oh, no.
Yeah, it's read-only. It's read-only. So why is it a wrapper? Anyway, so never write Python. Okay. Anyways, when you get one of these things back from Python, it should be like extremely suspicious to you that they're like nominally memory locations, but like there's something going on there, right? That's definitely a data structure. We're just looking at the binary encoding of the data structure. So now you saw this once in the case of exception processing. I think. Oh, this is completely unreadable. Here's my keyboard code. It's bad. Don't use it. Oh, is it in? Right. Okay. So we've seen segments floating around. We've seen the CS floating around, but we've had to alter virtual addresses, and we've had to separately alter kernel code or task stack segment registers at the same time, because in order to hit a fixed known memory address, we have to modify both the segment and the address itself, because all of the addresses are segment relevant, which is actually kind of cool. Okay, so what are we going to do? We're going to have a big idea. And the big idea is anyone who's writing anything other than an OS never has to think about the difference between virtual and physical memory. Is this true? No, it's not true, and the fact that it's not true is a huge security vulnerability. But this is what they tried to do. And it made sense to try and do this because you don't want to have to write assembly code every time you execute a print instruction. You don't want to write assembly code every time you direct something through serial print line and all that stuff. So we've abstracted away all of our assembly this term, the same way we want to abstract away the difference between virtual memory and physical memory. So everyone living on top of the OS, it looks like they're working directly with physical memory. They can't tell they're not working with physical memory because the OS is making it seem like they're working with physical memory. And then suddenly you look inside the OS and it's mass chaos and you're responsible for maintaining, that's right folks, a key value storage medium that is going to map virtual memory addresses to physical memory addresses. And further, you may have to manage this differently for different processes because you may have made different promises to different processes about the locations at which certain bits are living. So, instead of allowing a user-level process to directly access the storage device, instead, the OS, alongside the MMU, intercepts each of these memory requests. And I do so strongly think of it in the terms intercept because before 1978, it would have just been a literal lookup. When you ask to read something, it goes directly to the bus goes directly to the MMU sends you the bits back. No longer the case. Now, you make the memory address, the OS catches it before it goes anywhere and begins processing. So at the hardware-software interface, the OS and MMU will jointly manage a translation. Oh no! Oh no, I cut off my slides. Oh, it's so embarrassing. Which one of these went to an extra line? I think both of these went to 2 lines when I changed them. Also, I don't know if anyone knows how Firefox works. Why is this thing over here? Can I, like, turn it off? Wait, did that?
You just click
The thing at the
I
top?
don't know, actually.
You did. That's not better. Look at all this dead space. Isn't Dead Space a cool game? It is a survival game. Look, it's worse. It's a worse movie than it is a game. Okay. Okay, we got a little distracted there, but that's okay. Everyone understands. Okay. So for segmentation, the translation step is trivial. It is addition. So say we have a local memory address of 1234. Say we have a segment address of 1111. We simply perform, we compute a linear combination of the values, basically, right? And so then we look up location 2345. Easy. This slide says it is hard to keep track of virtual and physical addresses. The reason for this is usually you don't care which one you're dealing with because the OS is responsible for keeping track of it. And so it is easy to just say address and not specify whether you're talking about virtual or physical. A good way to think of this is that every time I've ever said address to you before this very moment today, I was referring to virtual addresses. Okay. So how are physical addresses distinct? Physical addresses are not software visible. They are visible only to the OS. Or perhaps to the hypervisor or supervisor. They're visible to the lowest level piece of code running on the hardware. And that lowest level piece of code running on the hardware will protect all higher level code from having to think about them. Physical addresses are unique. There are not 2 8 locations. There are not 2 1 2 3 4 locations. A number corresponds to exactly one location, usually within the SSD. If somehow a piece of software gained access or gained awareness of a physical address, different pieces of software could use the same physical address to look up the same thing. This is not true with virtual memory. So the physical address is where something lives at the hardware level. Virtual addresses are different. Virtual addresses are OS managed. They are translation dependent. If I run the same piece of code on 2 different operating systems, it may work quite well on both operating systems. It may make memory accesses on both operating systems, as every executable makes memory accesses. Those memory accesses are not going to be the same numerical patterns on different operating systems. And even if they were the same numerical patterns on different operating systems, for example, if you were doing everything by offsets, they would still correspond to distinct physical addresses once the OS translates them from the internal namespace of the computer, of the executable, to the physical, reference of the SSD. They are non-unique. I wonder if I can do this. Oh, right. So on this computer, I don't know why this is, if I open 2 windows of my terminal, both windows crash. So I can't do side-by-side terminaling, which is kind of too bad. So see how these numbers are different? 13959, 13459. Somehow every time Python loads up, it knows where print is, but print is not always at the same location. Guessing that's because print is in a library that isn't maintained by the process. So that library is in a different segment or page table, right? So I need to save a different offset for my different executables. The same virtual address in different programs and processes may refer to distinct physical addresses, and distinct virtual addresses may correspond to the same physical address. I claim this is something an awful lot like a virtual address. It is referring to something that must exist at a physical location. I certainly have the bits that correspond to the Python standard library on my device somewhere physically. So this refers to a physical location. And this is a different virtual value that refers to the same physical location. So that is 2 different virtual values referring to the same physical location. This means there's no bijection. Okay? Do you all know what bijections are? Okay, does someone who know what bijections are want to explain them? A biject, okay, yeah.
Well, it's a function that's injective and surjective.
Okay.
Every element of the domain is mapped to one element in the codomain, and every element in the codomain is mapped to one element of the domain.
Okay, and so why is...
Convertible function.
Yeah, and so why is this not a bijection?
Why is, what, I'm sorry. Well, because multiple things can have the same result.
Yes. So it's either not surjective or injective. I don't remember which one. It's
Injective. It's
yeah.
injective.
Okay. And it's not the other one either, but that's harder to demonstrate. If I were a good professor, I would know how to look things up by their ID, and I would look up this address in this memory space and hit a segfault. But I'm not going to do that now. I'm resisting the urge to do that. I successfully resisted. We're back. We're back. We made it. Ooh, that was touch and go for a minute there. Can you believe we've had this much fun already, and there's still 30 minutes of class left? I'm overjoyed. So fun fact about these visuals. I don't know if any of you think this is interesting. This is not related, I just feel like. So this is the image that's embedded there. If you look at this image, you'll notice it is black text on a white background, right? You will also notice that this appears to be sort of, perhaps, seamlessly blended into the slides, right? But, okay, here's another one. Paging. Here we have it again. So, what I actually did here, oh, it's so zoomed in. Okay, this is going to be unpleasant to display. Right. Oh, well, this is good enough. Okay. This is a HTML element where I did a direct image embed, and I applied a 0.9 inversion filter because I found out that my slide background, it's not actually black. This is 90% gray. So I do a 90% invert on this. I still perceive this as white, even though that's 10% gray. And it just so happens that probably, and I'm guessing there's a color science reason for this, usually I preserve a pretty good degree of contrast between this. And then it also has the benefit of not sort of like, the term I always heard was like flashbanging, when you put like a very bright thing up on your slide and like floods the room with light. So anyways, if you're ever trying to make dark mode slides and you use this template, if you invert 0.9 something, it blends. So that's kind of cool. Anyways, so what does this look like? I have virtual memory with some offset. What is the offset? 100 in this case. So 0 to 150 maps to 100 to 250. In this case, we have 0, 150. So this is, we argue the same process because it's using the same amount of memory. This one has an offset of 300, so it starts at 300 and goes to 450. Looking at this immediately, you should perceive that there is a disaster waiting in the wings, which is that I am using up my physical memory in chunks of size 150, and I only used 2 chunks, and I took up 3 chunks worth of space because this ends at 450. So this should seem bad to you. Okay, so we can imagine the same program runs twice or more, as I demonstrated with Python. Each time, it uses the address space 0 to 150, so local 150 addresses for some data. There is no collisions because 150 virtual address from the perception of each process corresponds to a distinct physical address. So those distinct physical addresses have distinct values in them, and so we are not corrupting each other's memory. Segments differ, so physical addresses differ, even though the virtual addresses are identical. That's cool. Now, this leads to one pretty nice thing, and this was the, I did not have you implement a subtraction linked list, even though I thought about it, because it seemed really hard, and I couldn't do it. So maybe you are all much smarter and harder working than me, which would be good. But when I was introducing sort of architecture way back at the beginning of the term, I talked about the difference between the Harvard and Princeton architectures, and one of them was, I think, called the von Neumann architecture, probably the Princeton one. And we talked about the idea of a stored program computer, a computer where the programs that it executes are just stored in memory as bits or as numbers, right? One of the benefits of virtual memory is that you can take a stored memory program, it can internally refer to memory locations, and if you execute it within the context of some virtual memory, All of those memory locations can be literal from the perspective of the program and perhaps more importantly of the compiler. So it is now dramatically easier to generate executables. These executables run inside some kind of sandbox provided by the OS. All of the memory addresses go through amicably. And now you can run multiple copies of the same program concurrently in different virtual and physical locations, and they can still hit all of their memory references correctly. That is extremely useful. So you can always consistently refer to internal memory locations. Now, what do I think is going on here? Let's do hex ID print, hex ID X. It seems awfully suspicious to me that this is a 12-digit hex value and this is a 6-digit hex value. What do I think is happening? I think this is an instance-specific internal virtual address. So there's a bunch of implied zeros here, and those are referring to the local namespace. This thing up here is referring to the global namespace, and that's why it's extended longer. So when the OS processes a memory lookup, it checks first the segment location and then the local location. And so those zeros are going to be virtually mapped to something else. Let's see, what happens if I hex ID print over here? Right. So perhaps this 520 is like in some way referring to some same distance internally from something. So I think you have are they both A520? No. I'm guessing print is 520 bytes from something, perhaps the start of its library or something like that. Okay. The differentiation between virtual and physical memory addresses makes segmentation powerful. I claimed this in terms of the stored memory program. I've claimed this in terms of protection. But it leads to a problem, and the problem is called fragmentation. Fragmentation is extremely easy to demonstrate. I sort of already demonstrated it. Here we have 550 units. I'm assuming they're bytes. They could be words. We have 550 units of physical memory. We have 450 units worth of demand of virtual memory from 3 different instances of a program, which use 150 units each, because of the allotment of the first 2 instances of the program. There is no memory region that the 3rd instance of the program can work within, even though there is sufficient physical memory to support 3 concurrent instances of the program. This is called fragmentation. Why? Because by placing in the segments, we create fragments, so something of the subsegment size, and these fragments are wasted. They cannot be utilized, or they cannot be utilized easily. There is no way to map the 3rd instance of the program to virtual memory without overlapping. There's no way. This is not of size 150, this is not of size 150, this is not of size 150. Is this feeling at all like the bin packing problem to you yet? Do you feel like you're packing things in bins? I feel like I'm packing things in bins. Do you all recycle? Yeah, right. Recycling might help. We'll find out, right? There is enough free memory, but it's not in the right region. It is not contiguous. Blog said continuous. I feel like I would not say continuous, so I said contiguous. So I'm using geospatial terms, and Blog was using mathematical terms. I guess that's fine. I don't think of regions as being continuous, personally. I'm going to show you a few solutions to this, and then I'm going to show you a way to prevent this problem from existing. One solution. When the 3rd instance of the program is dispatched, it sounds an alarm, and the OS goes out and starts doing OS stuff. And since the OS is allowed to do whatever it wants, one of the things it can do is it can take a currently running program and it can change where that program is in memory. This makes sense because the OS is the one that puts you at a certain location in memory when you start executing anyways. So we know the OS has the power to grant you certain regions of memory for your execution. So the new program is requested. The OS takes the existing programs and this is the technical term, it smooshes all of them together, right? So I learned in my cat parenting class I took on YouTube that when you're taking your cat somewhere where the cat may be stressed out, you're supposed to smoosh the cat so it feels safe. So that's what the OS does to its programs, right? Then you fit the new program in the open space, and that is how you adopt multiple cats at the same time, right? So I have my 2 cats. They weren't getting along that well, so I smooshed both of them, and then I placed the 3rd cat on top of the 2 previous cats. They all fit in memory, and I still have 100 left. This is easy. I'm allowed to do this, and hopefully I convinced you with my discussion of segmentation that it is no problem at all for me to move programs around while they're executing, because all of their memory locations are either inside of their own administered virtual memory and therefore offset based, and if I move the entire program, I move all the memory addresses with them, or they're somehow global and they're already being handled by the OS anyways, so that isn't a big deal to look them up. So this is one way to deal with the fragmentation problem. Now, here's a Calvin Tells Stories slide. When I was but a small child, and I was not yet weary of the ways of this world, I remember using Windows 95 and 98 to do something. It is basically impossible to guess what a child would be using for a computer in those eras, but I was using them for something. I was probably like trying to buy a laser on the internet. I suspect that's what I was trying to do. And one of the things you were supposed to do on your computer semi-regularly, and I do not remember what regularly means. And the other problem is I was like 5, so I didn't really have a sense of the passage of time. Do you remember being a kid and thinking the school year lasted like 100 million years long? So it turns out, like, this has to be true, right? So semesters are 14 weeks long, and they had to be 14 weeks long when I was 7, too, right? So how did it seem like I spent more time in school when I was 7 than I've been alive, right? But that's my perception. Okay, so semi-regularly, you were supposed to like open your operating system and like type in like defrag and or like disk cleanup. I might have one on here. I don't know. Disk cleanup. Disk use.
They might be in there.
On board. Anyways, now that I'm an adult, I defrag with command line tools like you're supposed to. But yeah, I remember clicking through Windows and finding a device that says defrag your hard drive, and then after you defrag your hard drive, your video games are like slightly higher performance for a few weeks. So that was cool. That's hard drive level, and that's not even solid state drive level, right? That was hard drive level. You can also defrag running processes, right? You don't have to only debug programs that you've installed on your device, right? The longer you go between defrags, the longer it takes to defrag, but there's also an initial startup toss every time you run this. So there's some sort of optimization theory idea where you should decide how often to run this. I see why the early OS designers left it manual, because it makes sense to ask the humans, like, hey, if you've noticed your computer slowing down, just run defrag then. That probably makes more sense than running it automatically. I'm assuming modern OSs are defragging all over the place in the background. I just tend to assume that if my computer is turned on and I'm not taxing it 100%, that Microsoft is doing something that I don't want it to be doing, or Ubuntu is doing something that I do want it to be doing. Do we trust Canonical, the Ubuntu people? Yeah. I don't think so.
More than Microsoft.
Well, we trust everyone more than Microsoft, except perhaps Amazon and Meta. I think I might even trust Google more than Microsoft. I've been waffling on that. Because, hear me out. Okay, so Google, corporate motto used to be don't be evil, right? Microsoft never had that motto, right? I've seen, everyone's calling them microslop now, right? That's great. You know, like, credit to the haters. You got to shout out the haters from time to time. Okay, downsides. Fun fact, think about how you would write an in-place defrag. It doesn't have good time complexity, is what I'm going to tell you, yeah. And also, like in 1978, right, these things all had finite write cycles on them, too. So you're blowing out your disk if you do this too often, right? I'm assuming there's still finite write cycles on my solid-state drive.
Yeah.
They told me when I bought one it was going to slow down. It hasn't slowed
I'm
down.
pretty sure you're not even supposed to defrag solid-state drives because they don't suffer the same problems.
Yeah, well, they're not geospatial,
Yeah.
right? Like,
It's not,
They're programmable. Yeah. You just like change a bit in some register somewhere, and then it's defragged. Which is why solid state is awesome. Shout out Samsung. Shout out SK, and shout out Micron. And Micron wants to hire you. Okay. Shout out Boise, Idaho. Where was I going with that? Okay, so there's this. So you've all heard of like the Ironman triathlon,
Yeah.
right? So obviously, has man in the name, can't do it, right? So then there's iron distance triathlons, which are the same distance but run by a company that isn't named Ironman. Anyways, there used to be one in like Pocatello, Idaho, or something, south
Yeah,
of Boise.
Pocatello.
Is it Pocatello?
Yeah, Pocatello.
Pocatello?
I used to live like 45 minutes from there.
Yeah. So
My mom went to school there.
there used to be a non-affiliated iron distance triathlon in Pocatello that I was going to do next year, and they stopped doing it. Oh, the weird Ironman people won't go to ones that aren't run by Ironman. So that's my Idaho story. Okay, and Jimmy's from there, or lived there,
I
or
live
whatever.
in Idaho.
Yeah, shout out Idaho. One of the best states that is spelled with 5 letters. And the state and the capital have the same number of letters, too. You can't teach that, right?
It's true.
They did that natty. I'm going to keep going. Fragmentation was bad enough that it killed segmentation forever. Paging! My throat really hurts. Okay. I lost 6 pounds this weekend, I think, due to dehydration. Never go to a baby shower. They don't. They only have, like, champagne at them, which does not hydrate you. And also, I'm not breaking edge. Okay, here's the idea. Okay, you're like, wow, this segmentation problem's kind of bad. What should we do about it? It's like, well, what if we make chunks of memory of a size in between words and all of memory, maybe even just logarithmically in between it, right? And then we don't move any of those chunks around, but we provide hardware support for regarding memory that goes across chunks as being contiguous, whether it's physically contiguous or not. So it is perceived as contiguous at software level. That's what I did. The virtual memory spaces are called pages, and the physical memory spaces are called frames, so a page corresponds to a frame 1-to-1. There is a bijection between pages and frames. Each page can individually be mapped to any frame, and you can change the mapping at any time. So, now what do? Now, I take my larger memory regions, and I say it is a sequence of pages, and the pages need not be contiguous. They need not have continuous addresses, perhaps. We can show how this becomes useful by looking at the previously fragmented memory space. So what do? Now, how are we able to cheat here? The specific manner in which we're able to cheat is we can take non-contiguous fixed size blocks and regard them as contiguous. There was already a block of size 50 and a block of size 100. We take a page size of 50, we divide the memory region into blocks of size 50, and then we're able to find sufficient 50s to dispatch all 3 instances at the same time without moving memory around. From the perception of, I don't know, this kind of looks like, we're going to call that milk chocolate color. From the perspective of milk chocolate, it cannot tell its pages are non-contiguous. It reads directly across the region, and the MMU simply gives the bits back in order. This is cool. It doesn't really make sense to me that this worked, but it does make sense to me that this works in RAM and SSD. Because in RAM and SSD, physical memory is not geospatial. So you just change some bit flags and it rearranges where these things think they are. I cannot imagine this ever working on a hard drive. Okay. I am required by law to disclose to you that there is in fact a downside to this. It is not in fact perfect. We do not solve every problem. Why is that? We unreasonably assumed on the previous slide that no one would ever ask for memory in an amount that is not a multiple of 50. So, we're back to the bin packing problem. You always have to round up in size. Okay, and now you're experiencing some trade-offs here because there has to be some non-zero cost to being spread across more than one page, right? It has to exist somehow. And minimally it has to exist when you're doing a block read. You have to get dispatched back through the page table every time you read across a page boundary, which means the OS has to wake up and run. So you're paying some kind of time cost. So what can happen is you might not fully use any of your pages. Internal fragmentation occurs because not every memory region is an exact multiple of the page size. In general, what does this mean? You can waste up to 1 page per running process. That seems pretty small to me because you probably have 1 million pages and you're probably not running 1 million processes. I suspect the extremely poor memory performance of tabbed web browsing has something to do with not using pages efficiently. That makes sense to me. I don't know. I made that up. Internal fragmentation, according to Blog, is unfortunate but often better than external fragmentation that occurs with segmentation. So we use internal when it's paging waste, and we use external when it's segmentation waste. I don't know that I believe it's better, but it is true that this is what's done. I would argue the reason to use paging is not because the fragmentation is better. It's because the programmability is better. You are more nimble, you are more custom, and it can be adjusted. So it is better to have software level control over hardware accelerated things. Okay, and now for our final topic, we're going to introduce the page table. Page tables are cool as heck. They're heckin' cool. They're as cool as a refrigerator, the inside of a refrigerator. They're as cool as a glacier in the winter. I'll stop. Okay. So probably some of you have some sense of what percentage of the total addressable memory in your device is used by a running program. Well, let's see. Somewhere in here I have target. I think it's target boot image. Bootloader, release, build. I don't know how this works. Where's my executable? Maybe it's here? Okay, so that's an executable. See this thing, bootloader? We can measure how big that is. No, okay. So that thing is this many bytes. That's 4 megabytes, okay? So my operating system, my executable operating system bundled with a bootloader for QEMU is 4 megabytes in size. I opened up my disk whatever earlier, and I have 457 gigabytes available. So a gigabyte is how many times bigger than a megabyte? 1,000, probably. Right, so if I say something is like giga-stacked, that's way better than being mega-stacked, right? So I could say like a sandwich is the big yum, or I could say it's giga yum, right? And that's like 1 billion times better, right? So I have an executable, and I would argue this is like a relatively large executable. I don't know, it's an operating system, right? This is 1/10,000th of the size of my available memory. So we go back to the slides. I'm saying potentially millions of pages. It makes sense that my operating system takes up 10 pages. My operating system takes up 10 pages. It's 5 megabytes in size, and I have a 500 gigabyte hard drive. That means I have 1 million pages. Potentially millions of pages is individually mapped to a frame. This mapping information needs to be stored somewhere. Do you all remember when I made you write malloc? Ah, that was so fun, where you were like mapping things to things. Ah, that was great. You just save the offset of something and it tells you where the memory is. Those were good times. I've almost thought about just giving that exact same assignment again because it was such great fun. What problem does this lead to? You learned this with malloc. Someone has to keep track of what's malloced, right? So what do we do? We can no longer just use the segmentation registers because there's only 6 of them and 3 of them are, you're not in charge of them, right? You only get the extra, the fextra, and the gextra. So what we did with interrupts and exceptions is the OS and the CPU had an agreement that when the OS came online, it would write to certain locations a lookup table. And that lookup table, in the case of memory, is going to be called the page table. And it is going to be a data structure that maps virtual addresses to physical addresses. And we can visualize it like so. We have some virtual memory. It maps to a page. Our pages are multiples of 50 right now. Pages are the virtual name. Frames are the physical name. So virtual page 0 maps to frame 100. So that's this line. And then there's permission flags or whatever. You can put whatever sort of metadata in here you want. And what is our core insight? What we see here is that we can have multiple pages at address 0, because we can map virtual addresses, and they map to distinct frames. So 0 maps to 3 different things. That's what a page table looks like. Okay. Each program instance has sort of one page table of its own that encodes its own virtual memory relations to the physical memory. This page table is left in a certain location in memory, and the CPU has to be informed of that location in memory. And the way that works is there is a special CPU register that stores that location. On x86, that is the CR3. A few weeks ago, I showed you a visual layout of the registers for x86. And on the far left side, there was CRs, I think, it was either 0 or 1 through probably 16, maybe 18. And I said some of these are important and used all the time, and some of them are not. CR3 is important and used all the time. So it was the 3rd or 4th, I don't know if it's one indexed, control register to be added, and it always stores the location of the page table. And when that register was added to x86, that's when there became hardware support for paging. So CR3, I call control register 3. Every time a memory address happens, it gets relayed through the CR3. So, how does it work? A running program, execute a save or load instruction. The CPU reads the save or load instruction. It determines first whether this is a local or non-local address. If it is a local address, it executes it via an offset. If it is a global address, it passes it through the page table. When it passes it through the page table, it sends the MMU a request to load a corresponding frame, because pages correspond to frames. Once the frame is loaded, then the CPU can perform the memory operations. This is identical to an exception. This is an interruption of normal execution in order for the OS to make sure something works. It is a hardware-only process once the CPU has written the correct page table address to the CR3. And then there are a series of architecture-specific features. So because the hardware is going to just be reading bits that are written by the OS, it is possible the hardware and the OS can have some agreement to support things like permission bits. So I say a flags field, read and write. A page table of length 1 million is going to take up a lot of space. If I am listing 1 million addresses, and my addresses are word size, which is 8 bytes, then I am using 8 bytes times 1 million, which is 8 megabytes. I just showed you what I claimed to be a fairly large executable that was size 4.5 megabytes. If it had its own complete page table at about the 1 million size, 2/3 of its working memory would be the page table. That's dumb. That's stop. That's crazy style. So we're not going to do that. Instead, we're going to do a trick that, and you'll never guess what this trick is. We're not going to do this because why would I have literally 1 million blank lines in my page table? That's not 1 million because it's divided by 50. Whatever 1 million divided by 50 is. 20,000. I don't know. That's a lot of blank entries. So some absolute genius, by which I mean probably literally the first person that looked at this ever. I don't know why multi-level page tables are considered this great innovation. It's like, hey, what if we put a page table inside a page table? Yes, obviously, it's a tree. Okay, it's a tree. So we have level 2 page tables. What is this? When you index into a page table, it doesn't actually tell you the page to frame correspondence. It tells you the location of the page table that tells you the page to frame correspondence. And I know what you're thinking. You're thinking, wow, that's crazy. There's exactly 2 levels. There's not. It's a radix tree at byte size. x86 uses a 4-level page table, and it's mostly using 32-bit addresses, right? It can address up to 48 bits. I don't know what to tell you. Everyone would not shut up about how clever multi-level page tables are. I cannot actually think of something more basic in the universe. See you Wednesday.
Class is over.
Isn't it? Did I make that up?
I didn't even realize.
You're just having so much fun? Put that in the course of L's. Put that in the course of L's. I was always surprised when class was... Wait, maybe that sounds bad. I was always unpleasantly surprised when class was over.